Okay, now in part two, we're down to the last two of these set operation problems, and I've given myself some space here, and I've rewritten the few terms that we found in part one of this worksheet for each of the sets A, B, C, and D. So down here, I have to do a Cartesian product twice, and then I have to find the intersection. And so this is just going to be a little bit of work because I have to give myself enough elements of these two sets where I can actually see where they overlap. So A cross B, remember, Cartesian product means that we want to give ourselves ordered pairs. So blank blank. Where the first element of the ordered pair, the numbers I'm going to write in these first blanks come from A, and the number I'm going to write in the second blanks come from B. So A has the numbers like 1, 4, and 7, so I'm going to spread these out so I have a sense for what the pattern is happening, because again, this is not going to be the final answer. I've got to do something else with this in a minute. So I want to give myself as much room as possible. So B has numbers like -1, 3, and 7 in it, just pulling them from here. Okay, and so I can see my first coordinates are going up by 3, my second coordinates are going up by 4, and I have every combination. I'll have 1 paired with 3, 4 paired with -1, everything you could possibly imagine where the first number's following that first pattern, the second number's following the second pattern. B cross, oops, what was the other one? C cross D. Again, see Cartesian product, I immediately write down ordered pairs. And now the first coordinate has to come from C, which are these guys. So these are these odd perfect squares. So my first coordinates are odd perfect squares, and again, they can be in there more than once and in any order. And my D are these numbers that start with 1 and go up by 6 every time. So 1, 7, 13, and again, I'll have pairs like 9, 13, 1, 7. Anything that pairs one of these first coordinates with one of these second coordinates is in here. So again, this is an infinite set. So the question then is, what what numbers are in both of these sets? What does the overlap look like? And so if I'm just doing this by looking at the patterns, this is the most challenging problem on this worksheet. So if you're having trouble sort of seeing it, just take your time. The best thing to do probably is write out more of these guys so you kind of have more room. But let's just pick something like we see the 1s and 7s come up. So let's think about this pair, 1, 7, for example. Ask ourselves, is it in both sets? So 1, 7 is in C cross D because the 1 comes from C and the 7 would come from D. So even though I didn't list it up there, 1, 7 would be in C cross D. A cross B, well, A has 1 in it and B has 7 in it, so 1, 7 is in A cross B as well. So that's a good example of an element that's in both the A cross B set and the C cross D set. I'll just pause it here if you want to think about a couple more, and then I'll write down 2 more once you've had a chance to think about it. Okay, so you may have noticed, for example, that the next number, or did we do that one? Yeah, actually we did a minute ago. We figured out B intersect D, and we had the number 19 was actually one of the numbers that we figured out was in B intersect D. So the reason that's significant is that in this intersection, we know that 19 is going to be a valid second entry in both B and D. So anything with a common 19, the 19 is a possible second coordinate in the C cross D set, and it's a possible second coordinate in the A cross B set. And so I could use 1 again, right? There's no reason I can't reuse the same element. But if you think about it, as we go through, what you're really doing is you're forming first coordinates that are common to A and B, or sorry, A and C. You need a first coordinate that's in both of those, And so we didn't explicitly write down A intersects C earlier, but we could have. We did something similar, right? We did A minus C. And then the second coordinate has to be something from that's common to B and D. So something from B intersect D, which we did write down as part of the previous problems. So so anyway, so that's basically the idea. That's what you're going to be looking for. The next number that another number that's in A intersects C is 25. It's not hard to see that 25 is going to be, remember these are going up by 3, so this is going to go 19, 22, 25. 25 is here. 25 is definitely here. So 25 comma 7 would be okay, 25 comma 19. So once we find something that's okay as a second coordinate or first coordinate, we can keep reusing it in all combinations. So anyway, so we can get lots of examples like that. This last one seems like it's worse, but really it's not. Remember, the idea is you see Cartesian product, and you should think, oh, well, this is just a set of ordered pairs. And so give yourself some ordered pairs with some room. And then the rule is I have to fill in the first blank with something from here, and the second blank with something from here. Well, that second set, that's just the natural numbers. So you can put 0, 1, 5, whatever you want in the second blank. So the second blank is just natural numbers. They don't require any thought at all. They're just any natural numbers at all. In the first blank, you've got to use elements from the power set of C. And so to do that, remember that's just sets that we're making using elements of C. Let's remind ourselves, C is these odd perfect squares. So elements of the power set of C will be just boxes that we could make. So maybe the set with 1 in it, maybe the set with 1 and 9 in it, be okay. And the empty set is also okay. So there are lots of examples of that. Okay, so moving on to section 4.1 problems, we have a bunch of relations, and the bottom line is to decide if it's a function or not, but mostly what these problems are about is reading the notation correctly. And so you should feel like it's the same kind of problem we just did. I need to get a good understanding of what pairs this is really defining. So this is a property description. It's saying include every pair that you can make that has the first coordinate from the set of integers, second coordinate from the set of natural numbers, but they have to make this equation true. They have to make this property true. So if I wanted just to test something, I could just erase this. Well, can I erase it? I cannot. Let me just get rid of it. Let me just give myself a few elements of z cross n, just to start with from that point of view. So -5 is a perfectly good element of z, 1 is a perfectly good element of n, so that's a possibility. 0, 0 is a possibility. -5, comma 0 is a possibility. 17, comma 1 is a possibility, and so on. So of course there's infinitely many of these things, but all I'm doing is forming ordered pairs where the first coordinate comes from here and the second coordinate comes from here. The question is, do any of these satisfy this property? And so to see that, I've got to think about the fact that I'm representing this in my notation using A for the first coordinate and B for the second coordinate. So this is really saying that the first coordinate squared is the second coordinate minus 4. So the first coordinate squared here is 25, and that's clearly not 1 minus 4. 0 squared, 0 minus 4, no. -5 squared is 25, no. 17 squared, 1 minus 4, no. So none of these guys will actually do it. But by checking each of these into this property, that should give us some insight into what will work. So again, let me just get rid of this. So for example, if my first coordinate was, say, 1, and I actually pause and think about it, well, my first coordinate is called A, so A squared equals B minus 4. It is possible for that to happen. It would require that B is 5. So this pair is in the relation R. Similarly, if I use -1 for my first coordinate, then again, -1 squared is 1, and so for this equation to be true, B would have to be 5. So that pair makes the equation true. Let's try a bigger number. Let's say, say I put in -10 for a. If a is -10, then this notation says -10 squared is 100 is b minus 4. So in order for that to be true, b would have to be 104. And so again, that's okay as a pair. So I can list a number of these things. This is R now. This is really just listing out some of the terms here. But the most significant thing is that no matter what number I'm using in my first coordinate, I seem to be able to find a second number that goes with it, and that second number I'm finding is unique. There's only one second number that I can find that makes the equation true given that first number. And that's exactly what it means to be a function. So in this list of ordered pairs, every possible integer will occur as a first coordinate, and for every one of these first coordinates, there's only one second coordinate that goes with it. So this is a function. Once we start to realize that's how we can read the notation, then it's actually pretty easy to do these. Again, I'll just pick some random first coordinate, say 3, and I'll ask myself, what does the second coordinate have to be? What does the b have to be in order to make this true? Well, the only way that you could make this equation true, if the a is 3, is if the b is -2. 3 plus -2 equals 1 is true. But notice that -2 is not in the set of natural numbers. So even though 3 -2 would make this property true, this is not a possibility because it's not in this set. We can't use something that's not in that set. So 3 -2 is not okay for an element. Well, what if we started with -3 as our first coordinate? Well, now, if -3 is our first coordinate, and that is okay, right? The first coordinate comes from a set of integers which allow negatives. If a is -3, then b has to be 4 to make this true. And -3 comma 4 is okay as an element of this set. -2 comma 3 will be another pair there. -1 comma 2 is another pair there. So you can kind of see how they're related. Now, is this a function? Well, no, we actually determined right off the bat that it wasn't because of this guy, right? 3 was a perfectly okay coordinate from the first set, so perfectly okay domain element, but it does not have a codomain element that gets paired with it. So input 3 has no output, even though input 3 is perfectly okay in the first set. So this is not a function. So I'm going to go ahead and post this step of this video, and I'll continue on the second page with the next video.